All right, good morning, everyone, and welcome to PureLine's webinar, Making the Right Choice, Chlorine Dioxide versus Monochloramine Systems for Secondary Water Treatment. We're thrilled to have you all here as we explore the differences between monochloramine and chlorine dioxide as it pertains to secondary water treatment and solutions for implementation. As we go through today's webinar, you will see that there's a Q&A feature enabled through Zoom, and you can submit questions through Zoom during the presentation. We'll have time at the end to answer these questions you may have, and there might be time in between if it's like a pertinent question based upon the content that we might stop and pause and answer that question live too. If you do have a microphone or the ability to talk through your device, there should be a feature to raise your hand, I believe, through Zoom, in which we can go ahead and enable you to ask a question live if you'd like to through audio. It's not required, but if that's preferable for you, you're welcome to do so. It's my pleasure to introduce today's speakers on this topic. Andrew Brink-Dopke is the Vice President of Engineering and Technologies at PureLine, where he's been instrumental for over 12 years. With a background in chemical engineering, Andrew leads all chemical engineering efforts at PureLine, specializing in new chemical process design and R&D for 2Chem, 3Chem, and electrochemical chlorine dioxide generation and delivery systems. His extensive experience and technical expertise have been pivotal in advancing PureLine's innovative solutions for secondary water treatment. Bob Sullivan is the CEO of PureLine. Under his leadership, PureLine has become a trusted provider of ClO₂ solutions across industries such as healthcare, oil and gas, food processing, and more. With extensive experience assisting hospitals nationwide in selecting and implementing ClO₂ systems, Bob brings valuable insight into choosing effective solutions for secondary water treatment. Now, Dr. Greg Simpson is a distinguished expert in chlorine dioxide with over 100 published technical papers and 15 patents in industrial water treatment, quite a bit. He's the author of Practical Chlorine Dioxide, Volumes 1 through 3, and most recently in September, Greg co-authored a paper available in the public domain, Chlorine Dioxide versus Monochloramine, a review. With a PhD in physical chemistry, Greg's expertise spans R&D, product formulation, and field research, making him a leading authority in the field of ClO₂ applications. Once again, you can submit questions through Zoom during the presentation, and we'll have time at the end to answer these, or maybe even during the presentation. With that being said, I'll go ahead and pass over the baton to Bob Sullivan. Take it away, Bob.
Thank you, Alex. Guys, welcome, welcome. Hey, we are honored, Greg, Andrew, myself, to be able to share this information with you. I'm going to run you through just a little bit of background on what we want to accomplish today. First of all, I think everybody understands that water treatment in hospitals is a crucial issue in today's market. Okay, this is something that you have certain hospitals out there that take this very, very seriously, and you have a group that don't take it so seriously, and everything in between. But what we know is that not doing this correctly can cost hospitals a lot of money. So what we want to do is really talk about how chlorine dioxide is a powerful selective agent that can really be a game changer for your practices. So let me kind of address the needs first. So the need for this: every year Legionella poses a severe health risk. You read about it in the papers, you see it out there. We know for a fact that hospitals, as soon as they get a Legionella hit, and with somebody being injured, in some cases death, they automatically put a $12 million loss on their balance sheet to account for what may be coming their direction. And if these are widespread enough, it's a very, very big issue. So Legionella is a very, very serious thing that needs to be taken care of. And again, we're going to kind of, with the experts of Andrew and Greg, we're going to kind of bring this together and then talk about how our chlorine dioxide solution might be able to take care of all your needs there. So today, let's explore how the chlorine dioxide will disrupt these pathogens effectively, and how implementing it as a secondary disinfection can add to a robust layer of protection. All right. So why do you want to listen to all of this? Why do you think I have something to tell you that is important? If your facility is striving to manage waterborne pathogens, we'll show you how chlorine dioxide offers a level of control that traditional treatments often lack. Now, again, this is very important. Andrew and Greg are going to go over, but in terms of what chlorine dioxide can do, we're hopefully able to show you some scientific proof about how this works and how it will benefit you. You'll hear about real-world results supported by the latest research and case studies, and we're going to demonstrate the reliability and efficiency of this treatment. Now, remember, this is not necessarily new stuff. The machines are getting, you know, more modern today with unbelievable reporting capabilities. In the next webinar here, you're going to gain an understanding of chlorine dioxide's unique chemistry and how it excels as a secondary disinfectant. So this is all about what you're about to learn, including its ability to penetrate biofilms and achieve lasting pathogen control. We'll also discuss the ease of dosing, very important, the application's best practices. I want you to pay attention to that because this is not necessarily all about chlorine dioxide. You're going to pick up some tidbits because chlorine dioxide is one arrow in your quiver to kind of protect your hospital. And we're going to tie this all together when we talk about some of the CMS guidelines and, of course, ASHRAE 188 standards that I think they've been out since 2017, if I remember correctly. Okay, so with that, we're going to talk about, I just did the introduction. Let's talk about the background of secondary water treatment, research findings on monochloramine and chlorine dioxide, sizing the chlorine dioxide generator, and Q&A. And remember, during the course of this, just raise your hand if you want to ask a live question, and we'll go ahead and stop. All right, so hopefully you're all familiar with this. September 2017, the Center for Medicare and Medicaid Services came out with their memo. And basically what they told you was healthcare facilities need to conduct a risk assessment to identify where Legionella could grow. Number two, implement a water management plan. And that's all as laid out by the ASHRAE 188B technically, okay? If healthcare facilities will not do so, they will not be eligible or receive any Medicare, Medicaid funding. So they're trying to leverage the fact that, hey, you're getting this funding, but if you're not going to take this serious and manage your water, then we're going to take it serious and not provide you the funding. So healthcare facilities must implement a water management plan. The Joint Commission started to audit healthcare facilities since 2022. And the CMS memo increased the demand for water hygiene technologies. Again, I can't emphasize enough that what I want you to do is not only listen to what we're going to talk about in chlorine dioxide, but just some of the other things on here because I think it'll be a big help. So let's talk about the supplemental disinfection technologies. What's available to you and what are we going to address today? So there's really three that are only EPA listed disinfectants for potable water. And please note that we're kind of focusing on that EPA listed disinfectants. You have chlorine, you have chlorine dioxide, and you have monochloramines. We're going to spend a lot of our time talking about chlorine dioxide and monochloramines, not so much chlorine. Your water, most of you on here, probably get water that is chlorinated from the city. Okay, it comes to you that way. We also very aware that even though it comes to you this way, that still doesn't protect you against Legionella. So that's why the focus is going to be on the chlorine dioxide and monochloramines. There are some other technologies, okay? These are non-EPA listed disinfectants. That's copper silver, some of you may be using it, ozone, and then there's a mixed oxidant system out there, which is, in my mind, it's really a sodium hypochlorite generator. So you're putting bleach in the system. We're not going to spend a lot of time on these. If you have questions, we certainly have information. But they are non-EPA listed disinfectants for potable water. And so we really wanted to focus on, kind of the game here. So monochloramine chemistry is usually produced on site as needed. There's no storage or highly concentrated monochloramine solution. Precursors are, as you might be aware, sodium hypochlorite and ammonia chloride or sulfate. And it's important to maintain this ratio. You'll probably hear this from Dr. Simpson. Some people put these in and kind of willy-nilly and say, okay, I got a monochloramine system. But if that ratio, pay attention to this, that ratio of the chlorine and nitrogen are not perfectly reacted inside that reaction chamber, you're going to have all other types of reaction that are not going to protect you against Legionella. And that's an important caution. You've got to watch those machines and make sure you maintain that. What is chlorine dioxide? It's a selective oxidant. It's kind of this yellow-green liquid ultimately. And when I say yellow-green liquid, that's probably from your perspective. From the chemistry of this product, it's really a dissolved gas. So imagine that I just leave a cup of chlorine dioxide on my desk. That gas, it'll be liquid, it'll be that green yellow initially, but that gas will slowly try to escape. As it escapes, the yellow green will, reduce in its color. And so what I'm trying to identify is, just the basics of it. It is it is one chlorine atom and two oxygen atoms. If you get down to looking at the little symbols off to the side here, and again, dilute, liquid, aqueous, and gaseous solution. It's easier for me to think about it as a dissolved gas. It's used in a wide variety of applications. The biggest one in the country is it makes sure that your paper is white. But more importantly, to what we do at Pureline, it is used in a variety of industries such as water treatment, food safety. A lot of food plants around the country depend on it to clean the water, so they can make anything from yogurt to cheese, etc. The oil and gas guys use it to clean up the water that has to go down an oil well. And healthcare. We've been in healthcare for 30 years doing this. So it's been around a long time. So our background. This is a chart. It kind of gets into some of the strength of chlorine dioxide and what it can do. The table that you see that talks about oxidation strength compares different types of oxidants to chlorine dioxide. And what I want you to take away this is chlorine dioxide has compared to the others, a lower oxidation strength. And why is that important? Because it prevents the corrosion. Okay. You get in some of these and you're going to get higher corrosion. They're not good for your pipes. Forget about the safety of potable water, but I'm just comparing these oxidants. But it is a very strong, effective, selective oxidant. What does selective mean? That means that it really wants to go after things it wants to destroy. If you put chlorine or sodium hypo into your line, it's going to want to chlorinate to everything. Chlorine dioxide is not going to do that. It's going to go, it's hungry for things that are causing you issues, the biofilms, the bacterias, etc. The primary reaction is a radical-free reaction and is independent of pH. Now, not so important for hospitals, but we have other applications where the pH goes high. If the pH goes high, you have to use more and more chlorine, sodium hypo, any of the chloramines products, etc. This independence on pH becomes a very, very big advantage for chlorine dioxide. I've already discussed that it's a dissolved gas, and it's probably the best thing in this whole list that we can talk about for penetrating biofilms. It is less corrosive. I pointed that out in the oxidation strength. And the final product, and this is what the EPA and your FDA guys like, the final product eventually returns to just chloride and oxygen, which means chlorine dioxide can be registered as an organic compound. Okay, so with that, this goes over to Greg. Dr. Simpson?
Okay, thank you. As Alex mentioned, a couple of months ago, we did a paper at AWT, Association of Water Technologists, and the paper compared chlorine dioxide and monochloramine and their effectiveness at in a large number of categories. And this was a review article. And it's what the science says. It's what the literature says about these. It wasn't opinion. It wasn't my opinion anyway. It was the opinion of a lot of other writers. The first category was the relative speed and efficacy of disinfection. Chlorine dioxide kills, inactivates bacteria very rapidly, second only to ozone in terms of its kinetics of disinfection. Compared to monochloramine, which is much, much slower. One of the references cited in the article was these people compared monochloramine's action with that of non-oxidizing biocides in terms of how long it took to kill things. So monochloramine acts like a bacterial poison. Chlorine dioxide acts like something that causes a heart attack. So it's that's the difference in the way of thinking of the speed and efficacy. The second area was biofilm penetration and removal. Chlorine dioxide is known to very effectively penetrate biofilm. Monochloramine can also penetrate biofilm. Chlorine dioxide inactivates everything in the biofilm. Monochloramine doesn't. There are things in the biofilm that it doesn't go after. Certain forms of Pseudomonas, and actually some of the references actually indicated that use of monochloramine caused certain bacteria in the biofilm to actually grow. Finally, chlorine dioxide is pretty effective at removing biofilm, while monochloramine does not remove the biofilm. It gets some of it, but not all of it. To illustrate this, we a while back, we were trying to work with the Center of Biofilm Engineering, which Montana State University, which is the premier biofilm research facility in the U.S. We wanted to fund some research where they would study this, and they didn't want to because they said literature was already full of stuff that said that, so they didn't have to prove it anymore. In terms of bacterial resistance, can bacteria develop resistance to oxidants, to chlorine dioxide or monochloramine? For chlorine dioxide, no bacteria has been identified that has shown any kind of resistance or ability to not be inactivated by chlorine dioxide. For monochloramine, a number, as mentioned earlier, a number of bacteria have been found that develop a resistance to monochloramine. This research article that we did was a review article, very well referenced. The paper is 20 pages long, 10 pages of it are references. So it's worthwhile getting. If you want to know more, it's worthwhile getting and reading because there's a lot of supporting evidence in that paper. Next slide, please. Okay, in terms of disinfection byproduct, chlorine dioxide really only has two. One is chlorite ion and one is chlorate ion. The chlorate is essentially not really detectable in the field. You have to use ion chromatography to even find it. Chlorite ion is regulated. It has some harmful effects. It's like cyclamate back in the old days when you had to drink 8 hours, a can of Coke every few minutes in order to get enough cyclamate in order to hurt you. And that's the same way for chlorine dioxide and chloride. The regulating agencies always put a factor like they did cyclamate, the chloride's regulated to 1 part per million in potable water. Monochloramine, in terms of trihalomethanes or haloacetic acids, chlorine dioxide produces way less of those than anything. Monochloramine produces fewer than chlorine, but it still produces some. But monochloramine produces a chemical called nitrodimethylamine. Nitrodimethylamine has been directly linked to cancer, and while it's not regulated yet, it will be probably within the next year or two. So in terms of byproduct formation and environmental impact, chlorine dioxide is better than monochloramine. When chlorine dioxide reacts, it produces mostly oxidation byproducts. It does produce a few organic halides, but way fewer than chlorine, and even fewer than monochloramine. In addition, research has shown that the organic halides that are produced are water soluble. That is, they do not accumulate in the fatty tissues of fish or aquatic organisms. Monochloramine and chlorine do. They produce hydrophobic byproducts. And so they will accumulate. They're sort of insoluble in water, or less soluble in water. They like to accumulate in the fatty tissues of fish, and so they will bioaccumulate. Next slide, please. In terms of corrosion, a lot of work has been done with respect to corrosion and chlorine dioxide, and it certainly depends on how the chlorine dioxide is made. But we did a paper not too long ago about work in the oil patch where we're using fairly high levels of chlorine dioxide compared to what we use in potable water. And in every system we treated, with the exception of just one or two, and still they were within experimental error. The corrosion was low to begin with, so it didn't matter. But in every instance, the corrosion rate went down. That is, the natural corrosivity of the water was such that the chlorine dioxide, when you fed chlorine dioxide, the corrosion rate after treatment was lower than it was before treatment. Of course, that's in the oil patch. It is aggressive to certain plastics, chlorine dioxide is, and so we are very careful about our material choices for making chlorine dioxide generator where you have the thousands of parts per million of chlorine dioxide. But in terms of its corrosivity at the use concentrations that you use in potable water, it will not be corrosive. Monochloramine also is pretty good in this regard. But if you've ever had a drinking water system that used monochloramine, your toilet flaps don't last very long because the monochloramine degrades them a lot faster than chlorine does. The last point has to do with operational considerations. One group that's cited and discussed in the paper, one group studied carefully a biofilm in an operating municipal facility, a drinking water facility. And what they found was that when people switched to monochloramine, they saw an increase in biofilm growth. And so every major municipality that has switched to monochloramine has outbreaks of nitrification. That is, certain bacteria will grow in that distribution system that produce nitrate. And nitrate is a regulated species. Nitrate concentrations as low as 10 parts per million have caused a phenomenon called blue baby syndrome, where the nitrate will actually compete with oxygen and the baby will turn blue. And they call that blue baby syndrome. The way they solve that problem is they treat with chlorine dioxide or add chloride to the system. And so chlorine dioxide is better on the distribution system in terms of nitrification than monochloramine. Next slide, please. Now I'll turn this over to Andrew.
Thank you, Greg. I appreciate it. Where Greg is obviously incredibly versed in the chemistry and the science behind chlorine dioxide. My forte is in how to make systems and design applications for real world use to make them safe, reliable, controllable, those types of things. So we participate in all sorts of water applications throughout the country, and chlorine dioxide is used anywhere from municipal water to be the primary treatment of the water before it makes it to the hospitals, secondary treatment of that water within hospitals and food plants and nursing homes to keep those water systems clean, well water treatments for metals removal, as well as treatment and disinfection of coli and other waterborne pathogens, wastewater treatment, cooling towers, and we do this at hospitals and nursing homes as well, cooling towers to prevent biofilm accumulation, which will degrade its effectiveness, and as well control Legionella, which, if you've seen in the papers, cooling towers, when they become infected with that, can then spread that Legionella virus via water droplets to those that are near the system and cause infection that way, as well as used in CIPs and wash waters. But we're going to primarily talk about secondary water treatment here, which is, it's called water treatment, but the purpose of secondary water treatment is to keep treatment in the water to clean the systems themselves, because it's the system that is accumulating biomass or pathogens in it, because though the water that came to it is treated, it's not sterile. There are still organisms in that water. There is methods for infection of the system via contamination and other sources. So eventually, almost any water system, unless it has a secondary water treatment to maintain levels of chemicals and other processes to keep those lines flushed and clean, will accumulate biomaterial or pathogens in it at some point. Next slide, please, Alex. So why are we talking about Legionella so much? Well, Legionella obviously causes Legionnaire's disease, which is very awful, and those people who are in hospitals are very susceptible to it. It also grows and lives within the biofilms. So if your system can harbor biofilm, Legionella is a naturally occurring waterborne pathogen that's in almost all water samples at very low levels. But if it's allowed to accumulate and grow in biofilms, that's where it becomes a problem. And then if it's in a site where you have immunocompromised or very old or very young that are exposed to that water, it can lead to disease. So remediating that biofilm is the primary concern. If you can remove the biofilm, the Legionella won't have anywhere to harbor and grow and accumulate. And biofilms are anywhere from something where you can open a pipe and literally see it, and there's slime or greasy substances, to just a slippery feeling on the inside of a pipe. It's not visible to the naked eye, but it's there. And bacteria is living in that. And that's where, when we talk about ozone and chlorine dioxide as being the only two dissolved gases as the listed disinfectants, they penetrate through those walls readily, because just like oxygen goes in and out of cell walls, so too do these chemicals, and they kill it from the inside out, and they kill them all the way down to the wall. Chlorine dioxide, a little bit better so in that it's not reacting with the metals of the pipe wall as extensively as like an ozone, and has a much larger half-life. Ozone is degrading and reacting with so many other things in the system so quickly that it's hard to get a residual to the point of use, which is what you need so that you have negative test results at your points of use, at your shower heads, at your faucets, those types of things. So you want to be getting a residual of your secondary disinfectant at those points so that you're killing anything that might start growing there. Next slide, please. So these are two, I think, really great case studies. Feel free to look them up, read through them in full, but in summary, it shows that incredibly low dosages of chlorine dioxide will control Legionella, and not just prevent it from showing up, which is a hard to track phenomenon, but remediate systems that have a Legionella problem. So the first study had a very small issue with Legionella, but by applying chlorine dioxide and maintaining it, and this is a key thing we'll talk about a lot. Shock treatments are great and can fix something for a very short period of time, but once you have pathogens or biofilms growing in the system, they will grow back. Eradication is almost impossible, so you have to maintain continuous treatment. That's the ideal scenario to keep your levels at or near zero detect. And so after 3 years of applying chlorine dioxide, the first facilities tests, they were at a non-detect level in all areas. Johns Hopkins, which we work with as well, and somebody may be online from Johns Hopkins today, I don't know. So hopefully they don't mind if we share it, but this is a paper that was done. They went from a 40% positives in one of their facilities, and after applying chlorine dioxide, within the first 2 months, they cut that positive rate in half, and a little over a year later, they cut that rate by over 90%. So it's obviously, it shows that it's not instantaneous, right? And you're not just killing it in the water. The issue is it's growing on the system, so you have to kill it back throughout the system, and only once you've done that will you see your rates really drop off. And so that's what we saw in these case studies that have been done. All right, so key aspect once you've decided, hey, I need a secondary treatment, I need to control this, I need to have a mitigating, is sizing the system. So chlorine dioxide is a good fit. Typically, we size for a 0.5 part per million dose to the water because these facilities are using a treated water source. The demand in the water itself is low. The system may be dirty or contaminated, but the water doesn't have any. So we need to get treated water with a residual throughout the system so that treated water is touching all these pipe walls and fittings and fixtures and killing any biofilm or pathogens that are growing there. And so the size of the whole system and the flow rate range really comes into play when in terms of sizing how much chlorine dioxide might be needed and how fast we have to deliver it. Next slide, please. So in terms of looking at total calculations, and we have some fantastic tools on our website. Off to the right is just an excerpt of our calculators that if you've got an application where you think chlorine dioxide might help, you can see what ballpark you're in. If we're talking about using pre-made chlorine dioxide solution and just dosing it with a pump, or if it's a large enough application where generation of chlorine dioxide on site is the most cost-effective solution, those types of things. So those tools are available, but the basic calculation is we look at total daily water usage, which you can calculate from just looking at the water bill, take the monthly usage and divide by 30. How much water you're using per day, multiplying it by the density of water, dividing out by 1 million, and that's the pounds of chlorine dioxide needed for a 1 part per million dose. As we talked about, a 0.5 part per million is typically a safe estimate. 1 part per million, it has some conservativeness in there if you want to be able to shock treat, if you need to. But an example calculation: if 50,000 gallons a year is being, or 50,000 gallons a day is being used, then applying the math, about 0.42 pounds of chlorine dioxide. That's active chlorine dioxide, not pounds of solution or anything like that. That's the actual pounds of the molecule that you need. But what's as important and more important in these facilities where typically we're treating the domestic cold water, which is on the fly treatment. If that water is going by one time, that's our only chance to treat it. We need to treat it based on flow. And in the mornings and the evenings, the flow rates are very high because showers, bathrooms are being used. And overnight, there's almost no water usage in a lot of facilities. So the flow rates can range dramatically, where the facility might have been using 50,000 gallons a day. Their peak flow may be 300 gallons a minute. And at 300 gallons a minute, we have to deliver that chlorine dioxide at 3.6 pounds per day rate. So even though we're only going to use 0.42 all day, we use most of that in a couple hour periods of time. So we have to size the pumps and the generation of the system, if it's a generator, to meet those needs. Typical water usage in hospitals, from what we found and in our experience, is 75 to 150 gallons per day per bed. So, again, another easy tool for sizing. If you got 250 beds or so, it's 25,000 gallons a day, 100 gallons per day, used as the average per room. And, you can do your chlorine dioxide calculations based on that. Dosing control, as I mentioned before, what we're looking for when we're treating domestic cold water is the flow, because that's the instantaneous read. We can secondarily control to the actual amount of chlorine dioxide in the water, because we have analyzers that can measure that. We call that trim. But because the water flow is changing so drastically and so fast, the only way to respond fast enough is that you're responding to the flow and proportionally dose the water and then adjust that based on the residual if you want. I would say in our applications, probably 50% do it solely on flow pacing, which is using the flow meter, and 50% use the flow pacing with a residual analyzer that then turns the pump up or down slightly based on how close they are to the target residual. They want to run 0.3 and it's running a 0.25. It'll increase the pump speed slightly based on the flow to get it close to that dose point. Hot water loops are a total different system. We consider that a closed loop. Water is added as necessary as people use water out of the loop. but that water is just circulating in that loop until somebody uses it. So we can't treat based on flow there. There you have to use a residual analyzer. And here is an advantage over like a monochloramine, where the monochloramine is only dosed into domestic cold water, and potentially a secondary point where they treat the water going into the hot water loop, but they can't actually treat the hot water loop because they're not measuring the levels of monochloramine, and you can overdose the system. With hot water loops, we monitor that level continuously, and it only doses as needed. So as new water is being used up to prevent that. So as I mentioned, right, there's the sizing calculators and how much chlorine dioxide are you really going to need, and that comes down to figuring out, hey, can I just buy pre-made chlorine dioxide solution? There's a few manufacturers of this, and we manufacture a fantastic product called Pure 3000, which is an organic certified 3000 ppm solution of chlorine dioxide. It's sold in anything from 1 gallon containers to 265 gallon totes, and a 55 gallon drum can treat about 330,000 gallons of water if you're able to maintain good residuals with a 0.5 ppm dose. So, doing that math, right? If you got a hospital and the calculations are coming up that you're using 20 or 30,000 gallons a day, then a single drum of chemical is going to last up to 2 weeks. And at that point, from a cost perspective, it's much cheaper just to buy pre-made chemical and have the right flow meters or sensors with, we have very high-end, accurate, reliable dosing pumps that will just deliver that solution into the water. So pairing that together is just as good as having a generator. Our HP generator makes the purest form of chlorine dioxide you can make. It's the same technology that's used to make our Pure 3000. That technology makes chlorine dioxide from sodium chloride and then strips just the gaseous chlorine dioxide and reabsorbs it into a clean water stream, so that the only product in there is water and chlorine dioxide. No byproducts from the generation, no acids, no caustics, it's pH neutral. And so from that standpoint, it's the least corrosive and the most effective in terms of its chlorine dioxide. If and when, so usually that break point is around a half to one pound per day. Once you're using more than that, switching to a generator is the right call from economics. You don't want to be changing out drums every day. Most places can't fit totes of chemical in to their facility, and even if they could, changing that on a weekly basis still a pain and quite expensive. So the generator takes the concentrated sodium chloride and produces the chlorine dioxide on site. So your container changeouts drop by a factor of 100, and you produce the chlorine dioxide only as needed. These are incredibly robust, safe machines. We operate in the basements of hospitals and nursing homes and utility facilities all over the country every day with these systems. And they're equipped with optical sensors measuring the chlorine dioxide that they're making, tremendous safety interlock systems, so they cannot be operated in an unsafe way. As Bob had mentioned, they come with digital reporting and data logging capabilities, remote communications to set up alarms. They can interface with the DCS the hospital has. The generators use Allen Bradley PLCs, so that usually is the same software being used in any data collection systems or management systems in the facility. So utility guys out there will identify that they can easily get any information they want off that machine for reporting or regulatory issues. Next slide, please. So this just kind of shows diagrams, and it's stuff that we'll help put together. This is an example of one where a hospital was being built. They shared the drawings, and we marked them up to show where to install general equipment. This is a Pure 3000 application with 2 injection points for hot water loops. So there's a sample cooler to cool off the water, run it through our PCA boards, which is our chlorine dioxide analyzer. And then that analyzer feeds the information back to the skid with the chlorine dioxide with the Pure 3000 dosing pumps to dose water into those domestic loops as necessary. Next slide, please. Another example, just something that comes with the generator or a little bit easier view of it, is the skids have injection pumps, reservoirs for holding chlorine dioxide, inject into up to most systems, it's up to 3 injection points. The HP generators, it's up to 6 standard. We can do more, but at that point, it's a fairly custom engineering, but that's not a problem. We do that as well. I would say the largest application at a hospital I think that we have has 4 injection points. That'd be a cooling tower, 2 hot water loops, and a domestic cold water treatment, which we do all out of one system. This installation is at a new hospital. This is one of 2 installations they actually have at that hospital. There's enough elevation change. I believe this is a 14-story hospital. So this is located on one of the lower floors, I believe floor 3, and it has the HP generator. So this is the electrochemical chlorine dioxide generation. The blue drum you see there, that's the sodium chlorite solution. So that drum will last that hospital. We change that drum every 3.5 months. So very infrequent change outs of the chemical. It's very cost effective to make chlorine dioxide with the generator once you have it. That chlorine dioxide generator feeds 2 points here. One is a hot water loop and one is their domestic cold water. So that's why you see 2 PCA boards that are measuring chlorine dioxide. The samples come back. The hot water pump turns on and off based on the reading, and the cold water pump runs primarily based on the flow signal that they're providing, with controls to turn it up or down or off if any error is detected or they get out of range with their treatment. This is that same hospital up onto the 7th floor, where they have 2 small hot water loops. So they didn't need a generator anymore, but they couldn't get the lines from the generator at the lower floor all the way up to this floor. So this is just a remote system to use Pure 3000. With this one, the hot water loops usage levels are so low that they're using a drum of Pure 3000 about every month and a half. So definitely did not warrant buying a generator. So this system has all the same capabilities. It just can't generate its own chlorine dioxide. It takes the readings from the PCAs. It controls the pump speeds. It has digital reporting, remote communication, all of that. This one has a built-in reservoir tank. So the drum of Pure 3000, which is the yellow drum you see there, is delivered. We have special fittings for our drums to minimize any exposure to the chemical. And so a special fitting called a drum quick is connected to the top of the drum, pulls out. There's a built-in dip tube already in the drum and can fill the onboard tank that allows the dosing pumps to continuously deliver chlorine dioxide. And there's no priming or having to swap containers on the fly and not have treatment or anything like that. All right, so Pure 3000, been speaking of it, so it's 99.5% pure chlorine dioxide, and what that means is that the chlorine species in the water, right? So different applications that make chlorine dioxide or chlorine, they'll have chlorine dioxide, but they'll also have chlorates and chlorites and chlorine and anything else, or maybe acids if acid is used. This, because of the stripping technology that we use, 99.5% of the species is chlorine dioxide. The remainder is a very small bit of chlorite, because dissolving chlorine dioxide in water will produce slight amount of the chlorite and a little bit of chlorides. Typically a non-detectable level of chlorine in the water. It's available in all kinds of container sizes. Down below you'll see just our primary containers and how much water they generally treat. So the tote of Pure 3000 can treat 800,000 gallons. This is the HP generator, as we saw in that other picture. It's NSF ANSI 61 certified, which is just certification for use on drinking water systems. So in terms of getting it through your state regulations, usually that's one of the things they're looking for. All the chemicals used, the Pure 3000 that's produced, as well as the sodium chlorite solution that we provide for the generator, is NSF ANSI 60 rated for drinking water, which again just helps meet those needs. Our pumps that are on board are built with 1,000-to-1 turn down ratios. That basically allows us to accurately dose that water from almost zero flow to the maximum flow rate of the facility without any spikes or dips in the residuals that could cause problems. As I mentioned, three dosing pumps can be built in. Typically, the HP generator can be expanded all the way up to 6 without any significant engineering. So there's no one size fits all, right? Not every place needs a generator. Not every place needs Pure 3000. Not every facility needs chlorine dioxide, right? You're developing a water treatment plan. You're identifying if you have a risk and what the right solution for it is. And secondary disinfection is good to eliminate problems. It's great for control, but the chemicals used, so chlorine dioxide or a generator, where you're dosing it, those are all important. But how to get that treatment everywhere throughout the facility and make it effective is just as important. And no one likes hearing that, but that is implementing the right plan so that your water systems are cycled and flushed on a regular basis. That dead legs, if there's construction changes and there's piping systems in the facility that are almost never used, everything that was connected to it is no longer in use, and so the pipe just sits there with dead water. We call those dead legs. That's where biofilm, bacteria, and pathogens will live and grow. And even if we're treating the rest of the system, no treatment's getting over into those dead legs, and they will eventually accumulate enough that when they start to slough off and recontaminate the water system, it may be too much at periodic times for the treatment level to adequately kill, and that will give you those periodic spikes in positives at your point of use. So identifying those areas, identifying the low water use areas of the facility and making sure to have a plan to cycle water through there, ideally once a day, but at least a few times a week to make sure that you get fresh disinfectant into those areas is very, very important to driving your positives to near zero. Ready to use solutions eliminate a lot of the headache. Speed to implementation. You want a system, they can be installed and ready to go in a week with the pre-made solutions. The generators are great to keep the cost down long term. Chlorine dioxide is easily measured, and when you're measuring it, unlike chlorine, where you've heard the terms total chlorine, free chlorine, we don't use those terms for chlorine dioxide because when you're measuring chlorine dioxide, it's chlorine dioxide, and it means it's in its active form because it doesn't change. The gaseous chlorine dioxide is the same in the liquid or the gas. It doesn't dissociate, which makes it easy to be sure that if I have a half part per million, that my system is going to remain clean or be getting cleaner every day with those levels. Next slide, please. All right, so the water system treatment fundamentals. And the reason I kind of changed it to say water system treatment is as I mentioned, we are applying the treatment to the water, but the water is really at that point, it's the carrier to help us clean the system, keep the system clean so that the system doesn't keep reinfecting the water at the point of use. Because that's really what's happening, right? No one's getting Legionella from the water coming from the municipality. They're getting it because the system that was now holding that water, building that they were in, has a problem, and it infected that water as they were going to use it. So that's our primary point of having that secondary disinfection. Flushing those lines, those unoccupied rooms, low use areas, dead legs. I know I talked about this all on the previous slide. This is the fundamentals of a water treatment plan. It's where you start. And testing. The testing plan, focusing on testing in those areas, right? Hitting a softball is really easy, but what we want to know is are those hard to get places being treated well, right? The chlorine could be doing great in lines where water is flowing all the time, nonstop. It's used every day. Yeah, you never get a positive there. But yeah, you go to the janitor closet on the 7th floor where they fill the mop buckets and stuff, and you test out of there, and it's almost always positive. Well, it's because that water is only being used very infrequently. But that's where you should be testing, because if you can get that to zeros, then your high use points are only going to be better. And the number of tests is important. What percent of your total drops are you really testing? Right? If you've got 1,000 water drops, in the facility, ideal test plan, you're testing 10% of those weekly. And then it's not the number of positives, but the percent of positives, right? If you only test 10 sites and you get 2 positives, right? That's a 20%. Expanding that to your total number is huge, right? So our goals are always driving that percentage drop. And that's how, when you read these papers that Greg Simpson has gone through, and when we look at our effectiveness, what we're doing is dropping that percent of positive readings. And the goal is zero, but in a lot of older facilities, a lot of old plumbing systems, that may not be an achievable goal, but we can drive it really close. But it takes consistent treatment and a consistent, facility operation and plan to keep those lines clean. Next slide. That's all I have.
Great.
Thank you.
Yeah. Well, thank you, Andrew, Bob, and Greg. Thank you for taking the time to share this topic for secondary water treatment. At this point in time, we'd like to move to the Q&A portion of the webinar. So if you do have a question, you have a Q&A tab on Zoom. Feel free to submit your questions through there. Also, you should have the ability to raise your hand if you would like to ask a question audibly. We can then unmute you and you can ask that. If you're uncomfortable with that, not a big deal. The Q&A feature is great. And I think we have 2 questions that came in. One of them, I think we actually answered via text first via Greg, but I might as well just kind of open it up so everybody can hear it as well. And Greg, so if you want to get ready kind of to answer this question as well, that'd be helpful. The question came in saying, what's a chemical interaction between ClO₂ and monochloramine if someone wants to add ClO₂ on top of chlorinated water coming from the city? So Greg, if you want to speak to that.
Okay, chlorine dioxide does not react with ammonia or primary amines. It reacts slowly with secondary amines and rapidly with tertiary amines. Monochloramine is a primary amine, so chlorine dioxide should not react with it. It'll react slowly with dichloramine, and if nitrogen trichloride were stable enough to last for very long, chlorine dioxide would react with it anyway.
Great. All right, the next question we have is, can ORP be used to monitor, measure, and control the ClO₂ levels in the potable water system?
The answer is yes. There is not a fixed relationship between ORP and ClO₂, because other factors in the water affect ORP. However, between 0 and probably a half a part per million, there is a very steep curve response between chlorine dioxide and ORP. You can develop your own curve because it'll be different from system to system. There is a body of work about ORP that says that ORP might be considered a better value for a better indicator of bacterial inactivation than chlorine residual. That was sponsored. There's a lot of work done by a lot of people, and the consensus was if you keep the ORP above 650, you hammer everything. But I'm not really willing to go out on a line and say that.
Well, and Greg, actually, when I took the company over 15, 16 years ago, all we really had was ORP. So the technology wasn't there. In today's world, 99.9% everything we sell is the PCAs, which are working really off of like a resistance or potentiometry. The ORPs are certainly available, but the accuracy that people are asking us today, it really requires that PCA.
Yeah.
Yeah.
That's put it.
Yeah, and yeah, especially here, this is regulated drinking water, right? And part of it is if you're using chlorine dioxide, right? Uh, you need to be testing for ClO2 and chlorate levels, in that water periodically. Anyway, and yeah, with ORP, right? pH has an effect on the ORP as well. You don't want to slip into, over treating the water and being outside of the regulation, outside of that 1 ppm range. So there are a lot of options now for chlorine dioxide measurement, and because you need to be reporting them anyway once you're using it, I would highly recommend a chlorine dioxide analyzer over an ORP in this situation. In dirty water industrial applications, ORP is often a much better sensor for telling you that you're at the levels you want to be at. But here I would go with a true residual monitor.
Yeah, a follow-up question, kind of related, I should say. Is there a known relationship with ClO2 and ORP? Is there an ORP level in the water that is considered safer, like the 650 to 50? So, that's good.
There's not. I mean, for any oxidant, as you add oxidant to a water system, the ORP will go up. For chlorine, the response is very good. For chlorine dioxide, the response is very good. For peroxide, it's not good at all. And I don't know about monochloramine. I don't. Well, I do. You can't really use monochloramine very effectively with ORP because it just doesn't get high enough. There's a paper that was written 20 years ago where monochloramine was trialed on a cooling tower, and we saw the ORP just wouldn't get very high. We could get up to a part per million of monochloramine with our feed system, but the ORP, it's risky to trust ORP with monochloramine.
Yeah, and Greg, I don't want to interrupt you here, but I thought about something else. It's still in the same vein of thought here. The reason you probably don't want to use ORP in these systems is there's already an oxidant in the water, right? We already know, like its ORP is already going to register fairly high because there's chlorine in the water, but that chlorine isn't really effective at getting through the biofilms. So that's going to cause a big interference in being able to understand what level is going to equate to what level of chlorine dioxide, and your chlorine levels from the municipality are not going to be consistent. So you're going to constantly be fighting that with your ORP reading, unless I'm mistaken, Greg.
I should point out that most of my experience is in heavy industry. So a lot of the things that I'm saying that apply to heavy industry don't really apply to the potable water market. Just for clarification.
So yes, with that, the sensors that measure chlorine dioxide are highly selective. They don't pick up the chlorine, so they're going to measure just chlorine dioxide versus ORP, as Greg has pointed out, it measures oxidants. So as those levels vary up and down from the city, you're not going to be able to differentiate chlorine from chlorine dioxide with an ORP sensor.
I think those were the only questions that came in. Bob, is there anything else you want to share before we conclude today's time?
Well, really, what I hoped you, all the listeners, were able to benefit from was basically a discussion of how you can improve patient safety, how you can improve regulatory compliance, and then I guess finally the fact that adopting a chlorine dioxide protocol will hopefully reduce your risk of outbreaks considerably, and you benefit it like the hospitals of Johns Hopkins, et cetera. Anyway, I'd like to thank everyone, and we appreciate your time, and I hope you learned something. If you have any questions, our email addresses are right up there on the screen, and you can certainly find us at our phone numbers on pureline.com. Thank you.
Have a great afternoon.